Hi everyone, myself Deepak from E-Content Development Center, Majlis Arts and Science College, Paramannur. In this class, we are going to discuss about the liquefaction of gases, how the gas molecules can be liquefied, and the theory behind this liquefaction process is actually seen through this complete video. For the liquefaction process, we have to do two processes. First one is the lowering of temperature and the next one increasing the pressure. So, what about lowering of temperature? What happens if you lower the temperature of a gaseous system? If you lower the temperature, then the kinetic energy of the molecules will normally be reduced, and then the moving capacity of the gaseous molecules gets retarded, and the gas molecules will just combine with each other during this process, because they will all come each other, and thereby there is a chance for liquefaction process. And then during that stage, if you lower the temperature sufficiently, and after that you need to apply pressure, high pressure, and on the application of pressure the molecules will certainly compress to form the liquid phase. So, these are the two main processes that we have done during liquefaction process, that is lowering the temperature to bring the molecules together and increase the pressure for the compression process that you have seen here. Okay. And now, here the scientist named Andrews, who studied the liquefaction process using carbon dioxide, and what he had found that there should be a minimum temperature, or there should be a range of temperature which is required for the liquefaction process. That is, in the liquefaction process there should be a name called critical temperature, that is named as the temperature above which the gas molecules cannot be liquefied and below which the gas molecules can be liquefied by the application of pressure, and that is critical temperature. So, that is represented as Tc in this term. So, critical temperature is defined as the temperature above which the gas molecules cannot be liquefied by the application of pressure. So, our first objective is to reduce the temperature, lower the temperature to the critical temperature. That is the first objective you need. And then after that, if you attain this critical temperature, then you need to apply a minimum pressure in order to start the liquefaction process, and that pressure is known as critical pressure Pc. It is defined as the minimum pressure required to liquefy a gas at its critical temperature. So, that is critical pressure. So, when you are applying this critical temperature and critical pressure, the gas molecules will start to liquefy, and the volume occupied by 1 mole of that gas is termed as critical volume, that is Vc. It is defined as the volume occupied by 1 mole of a gas at its critical temperature and critical pressure, and these three quantities are known as critical constants. And when you are applying these conditions, critical temperature and critical pressure, our gas system should be in a critical state. It should be in a critical state, and during this process the gas molecules are slowly converting into the liquid phase, that is into the from the area of high or low attractive forces to the area of high attractive forces, and that smooth merging of gas with its liquid is referred to as the critical phenomenon. And then this is the experiment which is actually done by Andrews on carbon dioxide. He tried to liquefy the carbon dioxide molecule, and look at what he had done there. You have seen lot of graph here, and these are actually pressure volume curves or isotherms of carbon dioxide at different temperatures. So, isotherms means say experiment which is done at constant temperature. So, what he had done here is that he started liquefying gas at 13 degrees centigrade to give this pressure volume plot, and then he increased the temperature to 21 degree, and also you got a similar graph there. And also when you are raising the temperature to 31.1 degrees centigrade, what is happening? The horizontal portion is getting diminished. Upon this process from 13 to 21 to 31.1, what is happening in this graph is that the horizontal portion is getting diminished during process, and this is actually what Andrews experimented. He plotted the isotherms of carbon dioxide for a series of temperatures, and now you need to look at the areas of this temperature, this curve. There are three areas present here. Here is the AB, here BC and CD, that we can look. What is happening in the curve AB? You are starting at A. You are starting at A using gaseous carbon dioxide. So, at A there is gaseous carbon dioxide. Using this curve AB, as moving from A to B, what is happening is that the pressure is getting increased and the volume is getting decreased. So, on the application of pressure, the volume is getting decreased during this AB, okay, and that is also again also in accordance with the Boyle's law, just like the Boyle's law curve, that is, as the pressure increases, volume decreases. And after that, what is happening? From B, when you are reaching at B, gaseous carbon dioxide is getting converted into liquid carbon dioxide, okay. So, at B, the formation of liquid carbon dioxide starts, and then during this horizontal portion BC, what is happening? The liquefaction process is actually starting, and gaseous carbon dioxide is converting to liquid carbon dioxide during this process. From B to C, more and more liquid carbon dioxide will be formed from more and more gaseous carbon dioxide. So, when you are reaching at C, what you are achieving is that the whole gaseous carbon dioxide molecule is converted to liquid carbon dioxide molecule at C. And then what is happening next? At the CD, the vertical curve, what is happening here is that the pressure is actually increasing quite drastically in that area. You are applying high pressure during that area, but is there any change in volume? There is not that much change in volume. What does that mean? That means in C, you are reached the liquid phase, and compression of this liquid phase is not that easy, and that is why as long as high pressure you are applied, the volume change is not that much. That shows the liquid is not compressible. And now we are looking at the totality of this isotherm. So, we studied these three areas. Now we are looking at the totality. So, what is the change which is happening from as we raise the temperature? So, the main change that you can see here is the horizontal portion. This BC is the horizontal portion. It is getting diminished from 13 to 21, and after when you are reaching 31.1 degree, what is happening is that this horizontal portion is just converted into a single point F, right. So, that is the point where actually the horizontal portion is the area where liquefaction is going on. So, at lower temperature there is a range there, right, but when you are attaining the critical conditions at or at the 31.1 degree, what is happening is that the liquefaction, this area is converted into just a single point. So, that is what happening here. And if you are applying higher temperature in that case, if you are applying 48 degree, look at the graph, what is happening to it? There is no such liquefaction point happening here. There is no such liquefaction. So, that means if you are applying a temperature greater than 31.1, there is no liquefaction process which is starting. So, that means you can say 31.1 is the critical temperature of carbon dioxide, and that is shown here. Look at 31.1, it is like a normal ideal gas curve. This curve is just a normal ideal gas curve. Isotherms below 31.1, you have three areas, right, and isotherm at 31.1, that means the gas cannot be liquefied at any high pressure. So, the critical temperature Tc is 31.1. So, this is the area or this is the maximum temperature that you can attain to liquefy the gas, and above that temperature you can't liquefy the gas. So, that means there is only gaseous carbon dioxide in that area, and below that you can have liquid carbon dioxide. Okay. Now, look at this isotherm EFG, and that is known as critical isotherm. So, that is 31.1 is your critical temperature, and the curve which connects this 31.1, this curve is known as EFG, that is critical isotherm. So, what is happening at F is that the liquid carbon dioxide, actually in this area you have gaseous carbon dioxide, and when you are reaching F, what is happening is that the liquid carbon dioxide will certainly start to form at once in a time. There is no range there. So, that means both the liquid at F, both the liquid and gaseous phases are quite, you can't distinguish between these two phases. That is, gas and liquid have the same density and they are indistinguishable, and that point is known as critical point, and the pressure corresponding to it is known as the critical pressure. So, why is this point F is so important? If you take this F point, you take two areas, to the left of it, to the right of it. To the left you can have the liquid carbon dioxide, because this area it is liquid, because after the horizontal portion it's all the liquid is formed, but on the right of it there is no liquefaction process. So, it will be gaseous carbon dioxide on the right hand side. So, this is actually what can I say, beyond F, the isotherm becomes nearly parallel to the vertical axis and marks the boundary between gaseous carbon dioxide on the right and liquid carbon dioxide on the left, and that is what is happening here. Okay. This is the Andrews experiment, and now what we are doing is that there is another scientist named Thompson, and Thompson analyzed the isotherms generated by this Andrews, and what he said that these all things are right, but in the case of horizontal portion and in the case of this is the isotherm that we have seen here, and what he told that the horizontal portion which is actually present in the Andrews isotherm will not be there. There will be a wavy portion in that area. There will be just a wave around that. You can't define the points. So, that is actually what is shown here. He suggested that there should be no sharp points in the isotherm below critical temperature. Okay, so that is all about Thompson's analysis. And now, what is the implication of this graph? This graph means this is also an isotherm at a constant temperature, and here the pressure is pressure is at the y-axis and volume is at x-axis. So, what you are seeing here is at a constant temperature and pressure. So, this is the pressure area. So, this is the line A, B, C points are there, and there is a corresponding pressure to it. So, for a given pressure and temperature, you can have different values of volume, right? This A, B, C corresponds to the volume, different volumes present there. So, that means for a given value of pressure and temperature, you can have 3 different values of volume at temperatures below critical temperature, and these 3 values are A, B, C. The 3 values, what happens to these 3 values if you attain the critical condition? All these 3 values will be same, and it will be the 3 values become closer as the horizontal part of the isotherm rises, and at the critical temperature all these values will be same, A, B, C will be same. So, from at this critical condition you can calculate the critical temperature, critical pressure and critical volume as well. Okay. And that is what we are doing. Okay. So, what we are doing here is using this condition, critical condition, we are deriving the expression for van der Waals constant or critical constants in terms of van der Waals constants. And look at here. This is the van der Waals equation for 1 mole of a gas, P plus A by V square into V minus B is equal to RT, which on expansion it will give you PV minus PV plus A upon V minus AB upon V square minus RT is equal to 0, just on expanding this. And then when you are multiplying this with the complete V square, what is happening is that PV cube minus PB V square plus AV minus AB minus RT V square is equal to 0. So, this is the equation that you are getting, and from these 2 terms we can have 2 V square terms here. So, collecting 2 V square terms you can write it like PV cube minus within the brackets PV plus RT V square plus AV minus AB is equal to 0, and that is termed as equation 1. Okay. Now, what you are doing is dividing equation 1 throughout by pressure. Throughout by pressure gives V cube minus within the brackets B plus RT upon P V square plus AV by P minus AB by P is equal to 0, and this is actually equation 2. This is the equation. See, this equation is a cubic equation. So, it is a 3 variable cubic equation, V cube is there. So, it is a cubic equation. Okay. And now we are applying the condition for critical. So, at the critical point you saw that there is only one volume for a particular temperature and pressure, there is only all these 3 values A, B and C become same, and it will be 1. So, at the critical point V is equal to Vc. So, volume will be critical volume, or you can write V minus Vc is equal to 0 or V minus Vc the whole cube is equal to 0. On expanding this according to A minus B the whole cube, you can have V cube minus 3V square Vc plus 3V Vc square minus Vc cube is equal to 0, and that is equation 3. And now, in this in the equation 2, we have already seen the equation 2 here. In this equation, what you are doing is you are replacing this temperature and pressure by critical terms, because we are applying critical conditions. So, temperature, pressure, volume all should be in the critical state. So, replacing T by Tc and P by Pc in this equation will give you this V cube minus within the brackets B plus RTC by Pc V square plus AV upon Pc minus AB upon Pc is equal to 0. Now, you compare these 2 equations. In both equations you have the V cube term first, Now, you have a v square term, a v term and a constant term. So, you just need to equate these two equations. So, in this equation you have the v square term of minus 3 v c, and here it is minus of b plus r t c by p c. So, if you compare this, you can write 3 v c is equal to b plus r t c upon p c, and then you are when you are comparing the v terms here, what is happening in the v term here, it is 3 v c square and here it is a by p c. So, you just write 3 v c square is equal to a upon p c, and then this is the constant term, that is minus v c cube, and that is equal to minus a b by p c. So, removing the negatives, we have the v c cube is equal to a b upon p c. So, these are the three equations that will arrive from these two equations. Now, on solving these three equations, we will get the critical volume is equal to 3 b, critical pressure is equal to a by 27 b square, and the critical temperature is called 8 a by 27 r b. So, these are the three equations which connects the critical constants with van der Waals constants a and b. Okay, so, this is all about connecting critical and van der Waals constants. Now, this is actually the theoretical explanation about the liquefaction process and the determination of critical constants. Now, how it is done practically or experimentally? So, now we are looking at the experimental determination of these critical constants. Critical temperature and critical pressure are determined using Cagnier-de-Latour's apparatus, and critical volume is determined using Amagat's method. Now, look at this Cagnier-de-Latour's apparatus. This is actually the apparatus. It is actually a U tube here. So, U tube which is attached to the bulb at the end, and in the bulb you take the liquid which is required to calculate the critical temperature and pressure. You take the corresponding liquid, and the rest of the U tube you will fill it with mercury in order to study the pressure variations. So, in the whole of the U tube it will be mercury, and at the bulb you have the liquid under examination, and the upper end is also sealed so that no air enters, so that it can be used as the manometer. So, this mercury column can be used to study the pressure. And then what is happening here? Here the temperature is getting raised in this vessel. So, the temperature of the bulb containing the liquid and its vapor is raised gradually using a heating jacket. So, as you raise the temperature, the liquid present in the bulb, it will start converting to vapor, and at the initial phases you can see the liquid and the gaseous state, the demarcation or the meniscus between the liquid and gaseous state can be seen initially. Upon raising the temperature to a limit where you can't see the difference between the liquid and gaseous state, and you should note that temperature. That is, on raising the temperature, a point is reached where the meniscus of the liquid becomes faint and then disappears, and the contents of the bulb becomes homogeneous, and that temperature and pressure is noted as T1 and P1. So, the boundary between the liquid state and gaseous state is getting lost upon raising temperature, and that temperature is noted as T1 and the pressure is noted as P1. Then you reverse this process, that is cooling process. If you allow to cool that system, again the meniscus will start to appear between the liquid and gaseous state, and you should note the initial temperature and pressure at which the meniscus starts to form, and that temperature and pressure is noted as T2 and P2. And if you take the mean of this T1 and T2, you will get the critical temperature, and if you take the mean of P1 and P2, you will get the critical pressure. Now, this is the determination of critical volume. Critical volume is actually the volume of 1 mole of a gas at its critical temperature and critical pressure. So, what is the problem in calculating the critical volume? You can't use any special apparatus for calculating the critical volume, just like critical temperature and pressure, because in the calculation of critical volume you should maintain the system at a critical temperature and pressure. Okay. So, one of the most accurate method is given by Amagat, and what he had done here, it consists of measuring the densities of liquid and vapor at a number of temperatures near the critical point and plotting these densities against temperature. So, suppose if you are taking carbon dioxide, we all know its critical temperature is 31.1. So, what you need to do is take a range of temperatures around this critical temperature, just like 30, 31, 32, etc., and measure the densities of the liquid and vapor at these temperatures, and then you plot it against density against temperature plot. And when you are getting these, so you will get two curves there for a gaseous carbon dioxide and for the liquid carbon dioxide. So, when these two curves are allowed to meet each other, then it will be the corresponding critical density. That is, when the two curves represent the densities of liquid and vapor are extended, the two curves meet at a critical temperature, since the density of the liquid and vapor becomes identical. Okay. So, this is the curve which is obtained on plotting the densities of liquid and vapor against temperature. So, temperature density plot is given here, and these are the two curves AB and BC are the two curves which are obtained upon plotting densities against temperature, and then they are allowed to extend at a common point B there. And now, how is this line drawn? That line is drawn like the mean values of the densities are then plotted against various temperatures, where straight line BD is obtained, which will be obviously pass through the critical temperature, which will be given by the point where this line cuts the curve AC. So, this line is obtained by plotting the mean of the densities at different temperatures. So, this straight line will certainly pass through this critical temperature line. So, at point B, what you are achieving in this point BD or in this line BD is that you are getting the critical density here. Okay. So, if you got the critical density, we all know density is equal to mass by volume. Okay. So, density is equal to mass by volume means you can have the critical density is equal to mass by critical volume. So, if you know the critical density here, from that equation you can get the critical volume. The critical volume is obtained by dividing the molecular weight of the liquid by critical density. So, this is the method to determine the critical volume. This is amalgam. So, this is all about the liquefaction process and how these critical constants are connected to van der Waals constants, and the experimental methods to determine. We have seen the experimental methods to determine the critical constant, the Cagnier-de-Latouche method and the Amagat's method. So, this is all about the theory behind the liquefaction of process. Okay, fine. Thank you.